Okay, in this video I want to talk about finding centroids for a section with a given density, constant density, and a constant thickness. This makes it a little bit easier, but this is, we'll start from the basics. So let's talk about a little bit of theory before we jump into an example. So let's say we have a cross-sectional area, some weird shape here. So now this, we'll say this is like a plate. It has a constant thickness throughout and a constant density. We'll just pretend that's constant thickness. So this plate is made up of all these small, we can break them up into small little sections, small little pieces. And the distance from, say that's the y-axis, this is the x-axis. The distance from the y-axis to this piece here, we'll call this weight 1, we'll call this weight 2, and then some weight I. So the distance from this piece 1 to the y-axis we'll call x bar 1. The distance from this weight 2, call x bar 2, all the way up to x bar I. And of course, this whole plate is made up of these little elements, right? Well, we know that there's going to be a centroid on this piece, so maybe it's right here. And this has some total resultant weight. Here, I'll draw it down further. So this is some total weight total. And the distance from this centroidal point to the y-axis we'll call capital X bar. That's the overall X bar, the center X location for this plate. Well, this capital X bar times this total weight, or total weight is going to be the sum of the little weights, so sum of little weights from I equals 1 to however many pieces there are, is going to be equal to the summation of all of these little X bar distances times the weight pieces, all the little weight pieces. So the sum of X bar times the little weight pieces is going to equal capital X bar times the sum of the weights. So this is from I equals 1 to n, however many pieces there are. And of course, again, this is equal to the total weight. Well, we know that weight is equal to the specific weight times the area times the thickness of this piece. Remember, specific weight is some weight per volume. So if we have the area times the thickness, we have volume. So we're going to end up with just weight. Well, we said that density was constant. So both the specific weight and the thickness is also constant. So these are both constant. That means your weight is proportional to your area. So that means it would be okay to substitute area for these weights. So that means we can, let's divide this summation over to the other side. So X bar is going to equal the sum of X bar I times WI. I equals 1 to n divided by sum of the weights, which are the summation of the little individual pieces. And again, we can replace, it would be okay for us to replace the area instead of the weight, because the gamma and the t is constant, so we can pull those out of here and they would cancel out anyway. So we can replace this weight with the area. So we can find our x bar, centroidal location in the x direction, on the x-axis using this equation here. And similarly, we can find y bar by taking the summation of the y distances to these individual small little pieces divided by the sum of the area. So let's do an example. So this is a composite section, sort of I-beam. So we're given the dimensions here, and we have to find the centroid, x bar and y bar. So right off the bat, by symmetry, I know that x bar is going to be right down the center, just because of symmetry. So I can skip a few steps here. And in order to find y bar, I'm going to set up a table. And I like setting up a table because it's easy for me to see, it's easy to organize. So my first column, I'm going to say shape. So I'm going to label, I'm going to break these this I-beam into 3 separate shapes that's manageable. So I'm going to break it up here, break it up here. I'll call this first one 1, call this piece 2, and I'll call this piece 3. So we got 1, 2, and 3. So what we're going to have to know from this equation up here, we're going to have to know the areas of each individual piece. So the area is going to be in millimeters squared. My y bar, I'm going to need to know, it's going to be in millimeters. And then if I multiply both of these, I'm going to find the numerator here. So I'm going to have a separate column for a times y bar. And this is going to be in millimeters cubed. Okay, so let's look at shape 1. It's 60 millimeters by 10 millimeters, so that's going to be 600 millimeters squared. For section 2, it's going to be 15 times 60, which is 900 millimeters squared. For this rectangle 3, it's going to be 25 times 10, that's 250 millimeters squared. Alright, oh, actually, before I started doing that, I should have picked out an origin. So now I can pick any point to be my origin, but I'm going to make my life just a little bit easier and pick the center of one of these pieces. And it could really be anywhere, but I'm just going to pick right here. I'll just say the centroidal location of that. So it's going to be right in the center of, so it's going to be 12.5 units over from this edge. So this is 12.5 or 12.5 millimeters from this left edge. And then since this is 10 millimeters tall, this is going to be 5 millimeters. Right? So I'll call this my origin. So this will be my X. And then this will be my Y. I know it's a little crowded. So for shape 1, which is this one here, the first one here, what is my Y distance from the origin? Well, we have to go up the 5 units, 5 millimeters here, up 60, plus another 5 to get to the center here, to get to this point. So that's 5 plus 60 plus 5, that's 70 millimeters from the origin, and that's positive. For shape 2, we're going to go up 5 millimeters plus another 30, so that's 35 millimeters. For shape 3, we're already at the center. So we're already at y bar, so that's just 0. And that's exactly why I picked the center of one of the pieces, so that'll be 0. So when I do this ay bar calculation, this will just be 0. That's just one less thing we got to do, one less thing we got to think about. So let's figure out 600 times 70 is going to be 42,000, and 900 times 35 is 31,500. And we're also going to need to know the summation of the area, which we're going to need to know for that part. That's going to be 1,750 millimeters squared. And we also need to know the summation of the area times y bar, which is equal to 73,500 millimeters cubed. So now I'm just going to plug and chug into this equation again. So my y bar, my capital Y bar, is going to be 73,500 divided by 1750. This is millimeters cubed divided by millimeters squared. And yes, that's good because these are going to cancel out. It's going to leave me with millimeter units, and that's what we want. And that should give me 42 millimeters. So what does that mean, 42 millimeters? So my Y bar from the origin that I picked is going to be 40. It's positive, so we're going to go up 42 millimeters up. So it should be about here, because we know this halfway point right here, that's 35 millimeters. So 42 is going to be, somewhere right here. So that's my X bar, Y bar. Capital X bar, capital Y bar. So that's my centroidal location. And just intuitively, it makes sense because we see that there's more area on the top half of this center line. So we know that from here to here, this distance is equal to this point to this point. So it should be above this center line because there's more mass, more weight due to this rectangle 1. So we know that the centroid is the center of gravity, or the centroid is going to be above this halfway point. So our answer does indeed make sense.